Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is meant for those students enrolled in college-level calculus courses, specifically Calculus 1, also known as Differential Calculus. If that's you, let's go.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
So here you are. You finally made it. Section 2.4 in your calculus textbook, the precise definition of a limit. You've probably heard maybe from other students that this is a bear of a section, and it can be. It actually can be pretty tough, but I have some visuals that hopefully will help out. I like to step my students through the precise definition of a limit very slowly, mainly because really strong understanding of what a limit truly is critical for calculus. So let's go ahead and dive into this. Example 2.4, number 1. You have, and by the way, this subsection I'm calling the narrow range definition of a limit, although it doesn't really matter. It's really a gentle introduction to a limit. So let's start by interpreting the meaning of the absolute value of x minus 3 being less than 0.001 or 1/1000th. The reason why I'm stating this specifically and wanting to investigate this a little bit is because this, again, is critical for our understanding of calculus. So the absolute value you should have remembered from maybe your trig or pre-calculus course. If you have the absolute value of a difference, which is what this is right here, and I'm just using A and B to keep it very general, the absolute value of a difference is really just the distance between those 2 points. So I'll go ahead and write that out. And so if you use that definition with the extra little bit that this is supposed to be less than, strictly less than, critical, 0.001 or 1/1000th, then you can glue that language together to say the following. And that's just using the actual language we have up above. And you can see I have a Desmos app that I have queued up here. But before we get into that, I want to show this on a number line. So you have a number line here, and you have a couple objects on it. One is the number 3, and the other is some value of x that you don't quite know. So I'm going to, in a different color, just throw a value of x, maybe right there. What we want to be true is that the distance between 3 and x, we want that distance to be less than 1/1000th. Well, that really truly means that x has to be really, really close to 3, within 1/1000th of 3. So there's a little wiggle room around 3 that we allow all of our x values that satisfy this inequality to exist within. So I'll showcase that. We know that, well, we have to imagine that we've zoomed in quite a bit, but we know that we have a neighborhood, is what I'm going to call it, of 3 plus 001, 3 plus 1,000th, and 3 minus 1,000th. That's our wiggle room around the center 3, and we require that the distance between x and 3 be within or be less than 0.001. Or in other words, x is so close to 3, it's within 1/1000th of 3. So let's visualize this using technology. Now you're absolutely welcome to use my technology here, and you could just go to the web address that I had there, and you can see that this aligns with this lecture. You can adjust A is the center, so I'm going to adjust A to be at 3. You can zoom in here, you can see I'm centered at 3, and this just allows us to see I have a bunch of values within a certain distance of 3. Right now the distance is a half. So 3 plus a half, 3 minus a half. There's a little wiggle room on either side of 3 there. But I could tighten that up if I want to. I don't want to go all the way down to 1/1000th because I don't allow that in here. But you can get all the way down to 1/100th. That's pretty good. So there's a good visualization of what I would call what most mathematicians would call a neighborhood centered at 3. But there's a little bit more to it than just that. So let's go ahead and explain how that can be used, that concept of an open interval there can be used to help us understand the meaning of this limit. Limit as x approaches 3 of the function 2x plus 3 is equal to 9. Since we already have the direct substitution property, or law, or theorem, whichever you want to call it, we already know what that limit really truly, how to evaluate that limit. We can do direct substitution because it's a polynomial and it does not have any domain issues at 3. However, that doesn't really give you a really strong, rigorous understanding of what the limit truly means. So, a lot of people will explain this by saying, well, as x gets super duper close to 3, that function gets super duper close to 9. I'll write that down. And that definition or that language is actually pretty fine for a general basic understanding of a limit. It is kind of true. As x gets really close to 3, our function does really get close to 9. However, that's not exactly what it truly means. So let's bring in some other visualizations here. Now, as you can see, I have the function 2x plus 3 mapped right there. And a little bit of text here. We're on our way to the true meaning of the limit f of x as x goes to a. Before we get there, we need to get more visualizations done. You're welcome to change f of x for this Desmos app, but the graph might not work as expected. It can work as expected, but it's just I didn't code it completely for that. Also, for the purposes of this initial exploration, we're going to assume that our function is defined at a, or is continuous at a, is probably a better way of saying that. So let's see, I've already centered it at 3, because remember, we're looking at the limit as x approaches 3 of 2x plus 3. And let's see, we'll use the concept of a neighborhood, the thing that I just had mentioned about that open interval. We'll use that concept of a neighborhood to marry the absolute value inequality that we looked at, x minus 3 being less than 0.001, to this limit. And you can adjust these values accordingly. So if you're not interested in that limit of that function as x approaches 3, you can do it as x approaches 2 or whatever you want. But I'm going to stick with 3 for now. Now, the idea that we all kind of agree with limits, as x gets really close to that a, that 3 there. So this means that you're creating a neighborhood about 3. A neighborhood is an interval with a radius. So the radius of this currently is set to 0.5. So it's 0.5 on both sides of 3. So it's 3. It goes from 2.5 to 3.5, and you can tighten that neighborhood up if you want to. So the idea is as long as we're grabbing x values from this neighborhood, even if that neighborhood gets really small, our y values for our function should continually get closer and closer and closer to that 9. And watch what happens when I do this. As I close that neighborhood, you do see that simultaneously we can find a neighborhood around 9 that also closes. And here's the deal. Our goal is to see that all the x values in that gray area, they're down below. So you'll forgive me if I say the x values in that gray area, when in reality, they're way down here on the x-axis. Right? So please forgive me if I say x values in the gray area. I really mean the x values that are on the x-axis from the gray area. But all those x values lead to y values on this curve within this red band. So all these are the y values, all these points correspond to x and y ordered pairs for this function, and the y values land within this band, this red band. And so that's kind of the concept that we first deal with when we deal with a limit, that as we pick values of x that get closer and closer to our limit of 3 there, the y values get closer and closer to 9. And you can see it happening there. So that's a visualization of what a limit is doing. It's squeezing the x values closer and closer to 3, simultaneously squeezing the y values closer and closer to 9. Of course, this is not exactly how a limit is, but it's close to it. Now, I don't know if you recall, but there is a slight issue with limits and the limit definition. With the limit definition, you are not required to have the function actually exist at a. So what I mean by that is we're allowing x to get really close to this 3 right here. Our function need not actually exist at 3, or if it does exist at 3, it could be a hole in our graph at 3 and be defined somewhere else. That's perfectly fine. Limits do not care about what the value is at a. They care about what the value of the function is near to a. And so to demonstrate that, I just have one other animation here. It looks almost identical to the one we just dealt with, except there's one subtle difference. The value of my function, I just created a hole in the graph at our point x equals 3, y equals 9. I create a hole in the graph right there, and instead moved that point up to 3, 11. Still, the definition of the limit should still ring true. That is, as x gets really, really close to 3, so as we squeeze our x values in, actually you can see down at the bottom here, see that 3 right there? As we squeeze our x values closer and closer to 3, our corresponding y values should squeeze closer and closer to 9, and they are. Now remember, we're never going to allow that neighborhood around x to be 0. X is approaching 3. It's never equaling 3. A lot of students, especially outside of college, a lot of students prior to college think, oh, I'll just sub in 3. That's not true. You're allowing x to approach 3 for this specific limit. By the way, if you want to play with this, the links are in my YouTube video down below. You can also move things around here. It resets when you leave. And you can make them wider. You could also change the function if you want to. So let's pretend that I want to make this 2 raised to the x. It will still work. Okay. And you could see that, again, I can make a wide neighborhood, and I could say, well, here I'm letting x approach 2. I could then tighten up that neighborhood as those x values get closer and closer to 2. You see, at least visually here, the y values seem to be getting closer and closer to 4. Which should make sense because 2 to the second power is 4. So anyhow, that's our second example, our second digital example for this sub example. Now let's go back to the lecture notes. Now, if you're learning out of the Stewart Calculus textbook, then in section 2.2, you likely ran into a definition sort of like this. I'm a little more rigorous with my definitions, and not more rigorous than Stewart himself was, but I will say that I do use some definitions that are likely a little higher level, but they're important. So in this case, I'm going to define a punctured open neighborhood. A punctured open neighborhood, now if you're a student of mine, you've already seen this, but a punctured open neighborhood of a point A is a set of all points within a non-zero radius of A. So in other words, you have this center at A, and then you have a radius, a wiggle around that A. Let's call that radius delta. So you have a radius A plus delta that gives you to a point A plus delta and to another point A minus delta. And we are going to require that as we inflate that radius, like you would inflate a balloon, that we're not going to include the endpoints. It's just a requirement of an open neighborhood. So this is what makes the neighborhood open. And we're going to call it punctured because we're not going to include A itself in the neighborhood. So all of the points within our neighborhood are everything from A minus delta to A, but not including A minus delta, nor including A, and everything from A to A plus delta, again, not including A and not including A plus delta. That is a punctured open neighborhood. Now, to be honest with you, in calculus, whenever the word neighborhood comes up, it really is a punctured open neighborhood. We're really talking about a neighborhood that has a hole right in the center of it. And this really works well with that idea that we were just working with, that limit as, I think it was x approaches 3 2x plus 3 is equal to 9. X was getting super close to 3, but as I was reiterating over and over again, we do not want X to actually be 3. We're willing to take an interval centered at 3 of X values, but we do not want our X values to ever become 3. That causes an issue, which you will learn about later on. Or you'll learn about later on. So that is critical for calculus to work well. And most people are pretty okay with that. Now I'm going to move into the last two definitions right here. These last two definitions are, at least on this page, are really just language conventions in mathematics. A delta and an epsilon neighborhood. Essentially, a delta neighborhood is a punctured open neighborhood centered at some point on the x-axis. So I tend to loosen up my restriction on language here, and I just say, listen, delta neighborhoods, these are x-axis neighborhoods. Okay, there is a slight thing I should say here. If your variable is not x, it's a horizontal axis neighborhood. And epsilon neighborhoods are neighborhoods on the vertical axis. Maybe I should write that, right? So there we go. And I should probably clean up this one over here and not call it the x-axis. I'll call it the horizontal axis. Perfect. So if you want to read these, you can. It just tells us that we have basically a punctured open neighborhood on the x-axis, and we have a punctured open neighborhood on the y-axis or vertical axis. That's what we talk about when we say we have a delta neighborhood or an epsilon neighborhood. And it's not a coincidence that I chose delta for this radius of this horizontal line or line segment. It is because it's a horizontal line segment and delta is associated with the horizontal. Epsilon is associated with the vertical. Just a language convention. And to illustrate this, I have a little applet. I think this part of calculus is so important to use a lot of technology to kind of really reinforce the concept. So let's go ahead and do that here. As you can read, it's time to focus on punctured open neighborhoods. These are open intervals missing their centers. In calculus, whenever you hear of delta or epsilon neighborhoods, we are talking about punctured open neighborhoods. There we go. Use the sliders below to look at delta and epsilon neighborhoods centered at A and L respectively. So A is the center for the delta neighborhood. So let's go ahead and move that so you can see that. I have it moving at spacing at 1. I didn't have to do that. I've just decided to. And then the epsilon neighborhood is centered at L. And this is going to work with our definition of a limit in a little bit. But the delta, which you cannot in Desmos define delta as the word to be a variable. So I'm using the letter D here. You can see that if I increase delta, well, there you go. The neighborhood increases. Or I could decrease the delta to decrease the delta neighborhood around our center of 2. Also note, I tried my best to put parentheses on that neighborhood so that you know that that is an open neighborhood. Also note, I put an open hole in the center of that neighborhood because, again, neighborhoods in calculus do not include their centers. So punctured neighborhoods, generally speaking. And we can say the same thing about this epsilon neighborhood that's centered at 2 currently. I use capital E for epsilon here because, again, Desmos does not allow me to write epsilon as a variable. So I can increase that epsilon neighborhood or decrease that epsilon neighborhood that's centered at 2. I can move the limit there up or down. I'll just move it up a few so you can see it up here. So it's centered at 4 now. And again, I can decrease or increase the size of that neighborhood. Pretty easy. Most people don't fall apart here. Nobody goes home and cries at this moment. That's reserved for later. Now we're back to the lecture notes. And here we see one more definition. As we move forward, our definitions get more and more rigorous. And I'm taking my time with it so that you get used to the layers of rigor that we're layering on this. So in this case, we say that the limit as x approaches a of f of x is equal to L means that if for any epsilon neighborhood, so that's the word that we've just introduced, so any vertical neighborhood centered at that L, so again, you can rewind the video and see we were centering our vertical neighborhoods at some value y equals L. They're called epsilon neighborhoods. So we say that limit is, well, no, it's not that we say that limit is true. We say that limit means that if for any epsilon neighborhood centered at y equals L, there's a corresponding delta neighborhood centered at x equals A, again, aligning to our conversation just a few moments ago, such that the graph of f is trapped in the boxed intersection formed by these neighborhoods. Again, except possibly at x equals A itself, because we don't care about the value of the function at A. Now, this definition is super close to being rigorous. However, it doesn't have enough to be very rigorous. So we're going to do another visual here because I need to kind of really get you on the same page as I am with the function being trapped in the boxed intersection. So let's go ahead and go to this link right here. And then after that, we'll come back and use that definition to re-explain the meaning of this limit. So here we go. Now you can see I actually have a completely different function because I'm not really worried too much about the 2x plus 3 for right now. I just want to showcase what I mean by the boxed intersection. So as we are on our way to figuring out the true meaning of the limit, before we get there, we need to get another visualization done. You're welcome to change this function to whatever you want, okay? So I'm going to center this. Actually, maybe I want to center it at 1, only because it's closer to the x-axis. It's kind of easier to talk about. No other reason. Notice that I have a hole in the graph right here at 1, 2. And I have replaced that point and moved it up to 1, 4. So this function actually has a hole in it, but the limit still exists. And the reason why we can kind of guess that the limit exists is because as we look at x values in this gray neighborhood right here centered at 1, this delta neighborhood, we can form an epsilon neighborhood, a set of y values, such that all of our x values from this delta neighborhood lead to our epsilon neighborhood. Now there is a problem with this. This example specifically showcases a problem with our layperson definition that we're dealing with. Let me see if I can maybe capture it right here. Okay. The delta neighborhood that we have is symmetric. It's centered at 1 and it wiggles by 0.32. So this is 1 plus 0.32 right here, even though it says undefined, and it's 1 minus 0.32 there. So it's 1 plus 0.32 and 1 minus 0.32. It is a symmetric delta neighborhood. However, as you look up here, this is not a symmetric epsilon neighborhood, and that's a problem. Epsilon and delta neighborhoods must be symmetric. They have to have the same the wiggle size for the epsilon neighborhood has to be the same above and below the limit 2 here. So it has to be, you see this distance between 2 and 2.5 is a half. And if it were a symmetric epsilon neighborhood, it would go to 2 minus a half down below, but it doesn't. And that is by virtue of the fact that this function, which is 2 to the x, is increasing very quickly as x gets larger. And so the epsilon neighborhood that this computer is, or this that Desmos is creating, is not symmetric. So that's a major issue that we have. But still, the idea is almost there, that we know I have a delta neighborhood about what we're allowing x to approach. We're allowing x to approach 1. Here's our delta neighborhood of size 0.32. And x values from those delta neighborhoods, or from that delta neighborhood, will lead up to y values within this box we've created. Again, a major issue with this box is that the horizontal red bar here is not symmetric around 2. And that is the major downfall of the unprecise definition of a limit. So we have to tighten up that language a little bit. But still, I hope you get the idea. As x gets really close to 1, y's get really close to 2. That's the layperson's definition. Okay. Let's tighten it up one last time. And actually, before we do that, I do want to mention that the definition we wrote down said that the limit as x approaches, in this case, 1 of 2 to the x is equal to 2, means that for any epsilon neighborhood somebody hands me, I can find a corresponding delta neighborhood. Well, they didn't actually hand me an epsilon neighborhood. That's the critical error here. Somebody did not just walk in and say, hey, here's an epsilon neighborhood. No, we have been this entire time adjusting the delta neighborhoods. But in reality, that is not what we adjust. Somebody comes in and hands us an epsilon neighborhood. That is concrete. And our job is to find a delta neighborhood that fits or captures the function in that little boxed intersection area. And we'll see that in the next animation, but I just want to say that out loud. And here we are back. And again, there's that definition. We're going to use that new definition, which is not exactly rigorous enough, but we're still going to re-explain the meaning of this limit using that definition. And in mathematics, when you're using a definition, you really want to try to stick with it as much as possible. So I'll rewrite a lot of this language. The meaning of the limit as x approaches 3 of 2x plus 3 equals 9 is the following. So here's the interpretation. For any epsilon neighborhood, you can see I'm just copying the language of the definition. For any epsilon neighborhood centered at y equals 9, because that's actually the value of the limit of the function, there must be a delta neighborhood centered at 3, such that the graph, I should color code those differently, right? Let me color code those slightly differently because I think that that's probably a good idea. So 9, I'll color in yellow, and then let's do maybe blue for that 3. 3 and 3. There we go. So for any epsilon neighborhood centered at y equals 9, there must be a delta neighborhood centered at x equals 3, such that once that's the case, we can have the graph of f get trapped in the boxed intersection formed by those neighborhoods. Now, again, the exception is we don't care what the value of the function is at 3. It could not even exist at 3. That doesn't matter to us. What matters is the value of all of the function at all x values near to 3. Now, the critical issue that we were having here is the fact that this whole definition starts with for any epsilon neighborhood centered at L. Okay. So in other words, we have to start with an epsilon neighborhood being handed to us. I'm going to write that down. So let me read this out. I said the issue is that the limit as x approaches 3 of 2x plus 3 equaling 9 implies that somebody's already established an epsilon neighborhood. And in all of the animations we've done so far, we have not had a pre-established epsilon neighborhood. We actually were able to establish a delta neighborhood, and the epsilon neighborhoods adjusted accordingly. In other words, the epsilon neighborhoods depended upon our choice of delta. But that's actually backwards. That's not the way a limit actually works. And I'll showcase this by going back to those animations in a moment, but let's go ahead and focus on this question. How close does x have to be to 3? Because this will actually drive what I'm trying to say home. So how close does x have to be to the number 3 so that the function is super close to 9? How close? Within 5/10,000ths. That's really the question. So when I say, let me go ahead and draw this out by hand, since I've been lazy and not drawn anything by hand. So in this case, again, we're limiting to the value of 3. I'll use blue for that. So we have x values approaching 3. So we have some delta neighborhood full of x values getting really close to 3, not necessarily at 3. And then we have a line that we're concerned with. I don't really care what it looks like. That's not that big of a deal to me. But we have a line. And we know, we just have some very intuitive confidence that the value of that function at 3, that's what we would normally say, is 9. And really what we're trying to prove is the value near to 3 is going to be 9. Great. In this case, though, this really illustrates the true definition, because here they're saying, how close do we have to get to 3? Because somebody just told you, I need my function to be really close to 9, like within this distance. So somebody has actually set the epsilon neighborhood, and this is going to be overly exaggerated, but that's okay. Somebody has set the wiggle room, the epsilon neighborhood, about 9. So this is 9 minus the epsilon, and this is 9 plus the epsilon. And remember, epsilon in this case was 0.00. I think there were 3 zeros and a 5. Let me double check that. Yeah. And this one right here is 9 minus that. So somebody has preset those distances away from the limiting value of 9. Our job is to find out how close do we have to tighten up? How tight do we have to ratchet this horizontal or delta neighborhood so that finally it's tight enough that all of its x values will land within this pretty, and let me use a color here for this, so that all of its x values land within this symmetric box. So we want to figure out how tight do we have to make x, get the delta to make that happen. So notice this is different than what we've been doing all along. All along, we've been adjusting the delta, and then epsilon was adjusting accordingly. So what I'm going to do is go back to the animations to showcase that. And honestly, all I really need is this one animation, because this will showcase what I'm talking about. This entire time we've been starting with, oh, I'm going to adjust delta, and epsilon has been adjusting accordingly. But that's not how this mathematics should work. It's that somebody concretely tells us epsilon, and we have to tighten up delta to make it work. So let me open up an applet here. And this is the very last applet I have for this. So we now get to the precise definition of a limit. The entire idea hinges on the fact that epsilon must be assumed as given. With this assumption, we are required to prove a sufficient delta can be found. So here's our function we've been playing with, 2x plus 3. Here's what we're allowing x to get close to, to 3. Instead of playing with delta, which is actually the opposite of what we should have been doing, we will play with epsilon and try to find an appropriate delta based on that epsilon. This is known as the Epsilon Gauntlet. Well, that's what I call it. Someone has challenged you and said, I bet you cannot find a small enough delta given this really small value of epsilon, and your job is to prove them wrong by finding such a delta. So let's pretend somebody walks in the room and they say, remember, the limit they think is going to be 9. And so they say, I'm going to give you an epsilon neighborhood of 0.5. There we go. They've now concretely told us the epsilon neighborhood, 0.5. So we have this wiggle about 9 of 0.5. So it goes from 8.5 to 9.5. That's that red band there. Notice our gray band, our delta neighborhood, is so wide that it contains our function. It has x values within this gray area that land on our function outside of that red bar. So when x is 3.352, which is within our current delta neighborhood, the y value is 9.704, which is beyond 9.5. So that's not going to work. So our job with this epsilon neighborhood that somebody handed us is to tighten up the delta neighborhood. And you can see I'm just showcasing how it's done. It's telling me the entire time, not good enough. So I'm going to keep tightening this up until it says, hey, you've done a great job. Notice, now if you look at this delta neighborhood on this, based upon the epsilon that they gave me, this delta neighborhood, all x values in this gray band from, I don't know what this x value is. Let's say it's like the delta value might be a 0.25. So it might be 2.75 to 3.25. all x values in there land within this region. Their y values do. And you can see it is almost a 0.25, isn't it? It's very close. In fact, if I click on it, yep, that's a 0.25. Yep, that's it. That's our delta as a 0.25 right there. That's our job. And now that you can see that, you can play with this. Just go to this animation and change the function all day long. I don't care. It's not that big of a deal. So if you want to call it, let's say 2 raised to the x, and then maybe I'll hop down here and say plus sine of x. You can create any function you want. Notice I have that little wiggle. Let me move the a value. Let's say that we're trying to find out. In fact, let me move it right here. Okay. And let's say that somebody comes in. Right now, it just happens that based upon the delta I had earlier, it's okay. But let's pretend that somebody tightens up this epsilon neighborhood. So originally, someone's going to walk in with an epsilon neighborhood, and they're going to do this. Actually, this one will actually work no matter what. Let me find a better one. Let me move this slightly. Where's my center? Right there. Okay. So somebody comes in, they say, okay, I see that you've already found this delta neighborhood's pretty okay, but I'm going to tighten up this epsilon neighborhood. So in reality, if somebody's going to challenge you with an epsilon neighborhood, it's not going to be a large neighborhood. It's going to be a super small neighborhood, in fact. So every time that somebody walks in the room, they say, here's an epsilon, 0.5. And you say, oh, that'll be easy. And you do some work. And then they're allowed to turn around to you and say, oh, no, I'm sorry. I meant 0.018. And you have to redo your work. Not really, but let's just pretend. And so your goal here, again, is to tighten up the delta here until you capture the function within the intersection of those two right there. And I kind of did, but for some reason oh, great job. There it is. So it did appear. And you could see that in this window, all x values from this gray neighborhood lead to y values within this red band. Now, you do not need it to be the tightest neighborhood. It's okay if it's slightly smaller, right? This is a sufficient delta neighborhood. And by the way, so is this. They're both sufficiently fine. But this is not, because you can see there are y values outside of that red epsilon band. This is the visualization of the epsilon delta proof for a limit. Now, before I end out this specific gentle introduction to the precise definition of a limit, I want to go back to the lecture notes and actually answer that last question that I asked. And here we are. We're just back here. I'm going to go ahead and erase all this. And now here comes the calculus-y question. How close to does x have to be to 3 so that f of x, which is 2x plus 3, differs from 9 by less than 0.005? So here's, if you want to now integrate all the language that we've had in this specific lecture, how close does x have to be to 3? That's an absolute value question. The distance between x and 3. We want that to be small. That's the distance. So this goes all the way back to the beginning of this lecture. That's the distance between x and 3. And we want 2x plus 3 and 9 to differ by less than 0.005. In other words, we want the distance between 2x plus 3 and 9 to be less than 0.005. So let me go ahead and point an arrow at that and say we want the distance between 2x plus 3 and 9 to be less than 0.005. And of course, we can translate that into mathematics. That's kind of the hardest part of mathematics, I think, for students, is translating language into mathematics. But at this point, you just got to kind of get used to it. So we have one piece of language we've translated into mathematics. We have another piece of language that we're about to. The distance between two objects is an absolute value. So the distance between 2x plus 3, remember, is you always use subtraction to say the distance between two objects. That's the beginning of this lecture. And you want that distance to be less than 0.0005. Now here's the deal. We want to know how close does x have to be to 3. So we're really asking, like, what is the maximal distance that x can be from 3? Like, how close are they to each other? So in other words, this distance, we want to know how tight is that distance. It's less than something. We just don't know what it's less than. Now, if you recall, again, from the beginning of the lecture, we called that distance a delta. It was a delta neighborhood centered at 3, right? We have this number 3. We have a bunch of x values near it, and we want stuff to be within a certain distance of 3. We want to get really close to 3. That is a delta neighborhood. We just want to know the distance between x and 3. We want that distance to be less than some delta. We don't know what that delta is. That's the big question of the day. What is delta if somebody hands me, ta-da, an epsilon? That epsilon there, and I want to convince you that that is actually an epsilon, because if you take a look at the graph, again, which I just erased, but whatever, you have this graph. We know that as x approaches 3, naturally, intuitively, we know that as x approaches 3, the output was supposed to be 9. But this black curve is my function f of x, right? I want the distance between that black curve and the number 9 to be less than 0.0005. In other words, I'm going to create a band about 9 of size. It was supposed to be symmetric, but I didn't quite draw it symmetric. Sorry about that. Maybe it'd be best if I start there. There we go. I want a band about 9 that's symmetric. 9 minus the epsilon, 9 plus an epsilon. That's an epsilon neighborhood. And notice the function right now is captured within this epsilon neighborhood. At least this part of the function is. Trying to highlight that part of the function right there. So it's within the epsilon neighborhood. So therefore, that's what I'm saying. Our function and our limit, that is bounded by an epsilon neighborhood. I want the distance between our function and 9 to be less than some epsilon neighborhood. And luckily, they've handed us an epsilon neighborhood. Now, here's the really cool thing about this. If you just do a little bit of algebra, and as I tell my students all the time, arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before calculus. So, a little bit of arithmetic here. This is 2x plus 3 minus 9, so it's minus 6. And a little bit of algebra, 2 times x minus 3. And you should notice something magical just happened, because I want to eventually end with an absolute value of x plus 3 being less than something. That will tell me what delta is. Whatever that something is, that's going to be my delta. And notice both of our expressions, our inequalities, have an x minus 3 in them. All I need to do is get that 2 to the other side. Well, you happen to know the absolute value of 2 is 2, so I'll just divide both sides by 2 on this one down here. And I'll have the absolute value of x minus 3 is less than 0.00025. That's half of 5 is 2.5. We still have 3 zeros in front of it. So that tells me, notice this inequality right here is identical to this inequality, with the exception that we didn't know what that picture was. We now do know what that picture is. We know that if we want our function to get really close to 9, and I mean super close, like within 5/10,000ths close, we will require that x gets super close to 3. How close? Well, this close right here. 25, what is that, 100,000ths? So really, really close to 3. And that is actually it's not just kind of, that is exactly the idea behind the precise definition of a limit. Somebody hands you an epsilon, and with that epsilon that they have handed you, epsilon's just a distance between the function and the limit. Somebody hands you that epsilon, you create an inequality with that epsilon, and hopefully somewhere with your arithmetic, you can come up with the distance between x and wherever x is approaching, becoming less than something. Whatever it's less than, that is your delta. That's the size of your delta neighborhood. X has to be really close to 3. That close to 3. You could do this with different numbers, by the way. I highly recommend that you try this. So you could change this language the following, and notice that I'm changing quite a bit here. How close does x have to be to 10? So that the function and 23 differ by less than 1/10. Now, the reason why I said 23 rather than 9 is because if you think about it, the limit as x approaches 10 of 2x plus 3 is 2 times 20 plus 3, or 23. So the challenge this time, somebody walks in the room and they say, here's my Epsilon Gauntlet. I'm telling you, the distance between your function and 23, so the distance between these two things, I'm requiring it's less than 1/10. I bet you that you cannot find a tight enough neighborhood around 10 so that all of those x values in your tight neighborhood around 10 will lead to y values that cause your function to be within 1/10 of 23. And you take up that challenge and say, well, okay, I will take on that challenge. I just need to find a delta neighborhood, right? So that the distance between, here's all about delta neighborhoods, the horizontal stuff, the distance between x and what it's approaching is less than delta. In other words, x is within a delta neighborhood of 10. Well, let's see how this works. Do some arithmetic. Now, I just made this up, and me making this up doesn't run any risk of this breaking. This will work fine. This is the absolute value of 2x plus 3 minus 23 is just minus 20. Divide both those, or factor out 2 out of both those terms, and I see this glorious x minus 10, which is where I want to arrive. I want to get it by itself within absolute values. So because the absolute value of 2 is 2, I'll go ahead and divide both sides by 2. I have the absolute value of x minus 10 must be therefore less than 1/20th. And so that tells me that if they give me this epsilon neighborhood of 1/10, I'll choose my delta neighborhood that's centered at 10 to be 1/20th in size. And any x value from 10 plus a 20th, that's not very symmetric, by the way. So 10 plus a 20th to 10 minus a 20th. All of those x values, except perhaps at 10 itself. Again, we don't care about the center. All of those x values will lead to the function, which may be way up here, but it leads to the function itself, where the function at the value of 10 was supposed to be, what did we say, 23? I'm going to have to move this, I think. There we go. So this height was supposed to be 23, where this lines up to. Sorry for my terrible drawing. All those x values lead to y values within an epsilon neighborhood surrounding 23 of size 1/10. So this is 23.1 up here. Whoops. It's supposed to be a 23.1, and this is a 22.9. So that is, again, the actual precise definition of a limit. Somebody hands me an epsilon, I am required to find a corresponding delta. If you can always do that for that function, that limit must be true. for any given delta. By the way, when we actually write down the true definition of the limit, it will be for any epsilon, not just for one epsilon, but for any epsilon somebody comes in the room with. If I come in the room with here an epsilon of 1/10, and tomorrow I decide to come in the room with an epsilon of 1/1,000,000th, you had better be able to prove it for both. And in the long run, you'll find just a good pattern for the proof. All right, that's enough for this specific lecture, just because you need some time to digest all that and play with those applets.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.